If you would recall, we have mentioned in the past that multivariable calculus is the easiest calculus because the thinking is already in play. We've gone through the hard work of starting to develop our calculus thinking, our calculus interpretations of things, and our calculus intuition. The process that we're in now is adapting that to functions of two variables, and then taking that beyond functions of two variables to equations in three variables, and then eventually to functions that have vectors for inputs and outputs. All right. So the good news is, of these three, we already have mechanics, and that's what we're going to be on about today. That's what I want to talk about today. I want to remind you that you know how to do lots of stuff. That's Calc 3 stuff that you've already been doing. So let's think about taking derivatives. The point is, we've got a lot of this already. Let's think about the process of taking derivatives. We're going to phrase some things that we know about derivatives that we don't always think about derivatives. We're going to take the things that we take for granted about derivatives, and we're going to make them explicit because we have words for things. We don't take anything for granted in mathematics except for the postulates, and no one would doubt those. So let's look at a couple of examples of derivatives, and we're going to start really small. So for example, what if I give you f of x is equal to 5x to the third? Actually, I don't want to do 5x. I don't want to just say f of x. I want to say y. I'll use two variable type, not so much function type. What is the derivative? I'm not kidding. What is the derivative of 5x to the third?
15x.
15x squared. We do nx to the n minus 1. We do nx to the n minus 1. That was our first derivative shortcut way back in Calc 1. Set the Wayback Machine to the halcyon days of Calc 1 when life was simple. And you learn the derivative, the definition of the derivative, and it's like, oh man, this feels like algebra because it was a lot of algebra. And then like the next week, your instructor was like, oh, nx to the n minus 1. And you're like, oh, motherfucker, why didn't you tell us this in the first place? So we know we're using an nx to the n minus 1. Why did you just, what did you do with 5? You just multiplied it by the 3 because the 5 just hangs out. The 5 just hangs out. So the derivative, we would write here, we would say dy dx is 5. I'm going to write it out in extra pieces. 5 times 3x squared. So the 3x squared part is us doing nx to the n minus 1. The derivative with respect to x of x to the n is nx to the n minus 1. We multiply by the exponent, we subtract 1 from the exponent. The reason that the 5 just hangs out is that we know that the derivative is a linear transformation. The derivative is a linear transformation. For those of you who went through linear algebra, that's the linear transformation that we talked about. For those of you who haven't gone through linear algebra yet, that's the linear transformation that you're going to be talking about. Linear transformations respect scalar multiplication. That's scalar multiplication. So the derivative is a linear operation, transformation. The derivative is a linear transformation, so the derivative respects scalar multiplication. that is the derivative of a constant times a function is that constant times the derivative of the function. The 5 is constant. We multiply that constant by the derivative, 3x squared. So if I had some other constant out there, like k, the mortal constant, what's the derivative? dy over dx. We do the same thing. We multiply by 3, so it'd be 3 times whatever k is, so 3k x squared. I forgot to write the answer here. That's why no one wanted to say 3k x squared, because I hadn't written 15x squared. I looked at 5 times 3x squared. It's like, oh, no, you got to finish that one first. Derivative of a constant times a function is that constant times the derivative of the function. What would be if we go the other direction? I was going to say we're going back, but we're not starting where we ended up. So we're just going back. We're just going to go up from where we started. And if we want the antiderivative of 5x to the third, what's the antiderivative of 5x to the third? 5 over 4 x to the fourth plus some constant. Differentiation and integration are not quite inverse operations because of that plus c. Too many things map to 0. Every constant, the derivative of every constant is 0. So we get a plus c. We don't know what was there unless we have some extra information. But they're almost inverse operations. But we know how this works. If we want the antiderivative of 5x to the third, the antiderivative of x to the third is 1/4 x to the fourth, and then we put a plus c because the derivative of every constant is equal to 0. Note that the same thing happened here. If differentiation is a linear transformation, then going backwards is also going to be a linear transformation. Integration is also a linear transformation. We just carry the constants along. When we have a constant, we just keep it. We just use that constant and scale up the antiderivative or the derivative. I won't leave this one hanging. You would probably write this 5/4 x to the fourth plus c. Whatever we have hanging out as a constant, we just carry it along. We just use that to scale the result. If we had some other constant, we would just carry that. I spelled K wrong. No longer 5, it's the mortal constant K. Oh wait, 4 was right. There's a lot of ways that we might phrase this. We ignore the constants, we carry the constants. We have internalized the idea that the derivative and the antiderivative is a linear transformation and that it respects scalar multiplication. We've internalized that concept. The reason that I'm calling it out right now is that we need it in a moment because we've moved on to multivariable calculus. And we want to recognize that we're going to use the same moves here that we did back in Calc 1. Any questions? How's everybody okay? Did your calculus teacher say that differentiation was a linear transformation? Or maybe they called it a linear operator? Even if they did, we wouldn't remember at this point. So it doesn't matter. This would be a day that I would save when I get guest professor Dwayne "The Rock" Johnson to cover class. He doesn't answer my emails anymore. So, because what I want to do is get like famous people to cover my class for me. I wouldn't make them learn any math. They would get to if they didn't know it, right? I don't know what Dwayne "The Rock" Johnson's experience is with calculus. So he'd like wear a little earpiece, and then I would give him a script because he's an actor. He could do that. He could act. And then if y'all ask a question, I would be listening from the other room. And I'd just be like, all right, what you gonna say? And then I would just feed him his lines. See how? And it would be excellent. I wouldn't let him use this. He would have to, at some point, be writing like this with his back to you. You can't see this at home, but this doesn't work on radio. He'd be writing like this, and then you would ask a question, then what would he do? Because it's Dwayne "The Rock" Johnson. What would happen if you asked him a question with his back turned to you? He would turn around, and then what happens? Eyebrow goes up, right? That's why he doesn't get to use this, because it would be less dramatic. It's way more dramatic if he's like here, then you say, oh, but Professor Johnson, where does that plus C come from? And then that's what it is. I don't know what it sounds like when his eyebrow goes up. I don't. My hearing's not that great. Now I just want to get a whole sequence of celebrity guest lecturers. Today we're going to have Professor Samuel L. Jackson. He swear even more than I do. Be awesome. That was all stalling for you to get this loaded into your subconscious, so it's running in the back. Here's what we want to do. What I want to demonstrate to you is that you already know how to do this for functions of more than one variable. I'm going to write a function of two variables. We're going to think about what the derivative means, and then we're going to decide what to do. One of the things that we're trying to avoid here is mechanics getting in the way of our understanding of things. We want to avoid the mechanics getting in the way of the understanding of things. I still want this one here. So I'm going to write down a function of two variables. We're going to think about what the derivative represents. So z is going to be 5x to the third times y to the no, just y. Y is fine. That's fine. That's fine. No, I need an exponent. I need an exponent. Y squared. Let's think about derivatives when we have two variables. Let's think about that slope, the slope of a line tangent to a curve at a given point. Think about derivatives. Yesterday, we upgraded slope of the line tangent to a curve at a given point to the equation for a plane tangent to a surface at a given point. Because a linear equation in three variables is going to be a plane, where a linear equation in two variables is a line. When we have that equation of a plane, z equals z naught plus m times x minus x naught plus some other m times y minus y naught. We end up with two slopes. One of them was the change in z with respect to x. The other one was a change in z with respect to y. So recall the equation of a plane is z naught plus m times x minus x naught plus, let's use with n times y minus y naught. M is how z changes with respect to x. So m is a dz dx. N is a change in z with respect to y. We know this is how it works. I know this because y'all have done this calculation. I gave you a table of values. You read the dz dx, put that as the coefficient of x minus x naught. You read the dz dy, put that as the coefficient of y minus y naught. You might not have even been totally sure what you were doing at the time. At that point, instinct had taken over. You were starting to do things automatically. And that's why I'm pointing it out so much right now. Because we need to take the thing that we might have done automatically and make it not automatic so we can understand what the F is going on. So when we calculated dz dx, we just ignored what was going on with the y. We just looked at that one row in the table. We looked at one row in the table to figure out how changes in x made changes in z. So think back to the table. We looked at one row to figure out how z changed with respect to x. Think back to the table. In the table, we looked at one row to figure out how z changed with respect to x. Everybody remembering it? Take a moment and remember it. I'm reading your minds right now. Some of you aren't remembering it. Okay, now you all are. Now you all remembering. On that one line, we looked at z changes. Every time x increased by 3, z increased by 2. What we were doing when we were looking at one row, in that one row, the y value was always the same. In that one row, y was being held constant. In that row, y is constant. In each of those rows, y was being held constant. That brings us to the business of today. We want to think about derivatives. We know that derivatives are slope. We know that if we have a function of two variables, we are looking for two slopes in our linear equation, a dz dx and a dz dy. The way we figured out dz dx is to keep y constant and see how z changes with respect to x. So now we're going to do that same thing. 5 is constant just because it's just 5. That sounds very dismissive of 5. I'm sorry, 5. You are valid and a very important number. And everybody likes to multiply by you. 5 is constant. What we're going to do is we're going to find the derivative of z with respect to x And that means we're going to keep y constant. So 5 is constant. We're going to imagine we're going to think of y as constant. We're going to imagine trying to find dz dx along each row of y. Y is always fixed. I want to know how z changes with respect to x. With that in mind, and without knowing anything other than that, what would delta z delta x be for 5x to the third y squared? Y is constant, so it's just y. We're going to think of the y the same way we thought of this k up here. But instead of writing k, we're writing y squared. That's fixed. Fixed value of y, fixed value of y squared. What's the derivative of x to the third with respect to x? 15x squared if we include the 5. What we're doing, the derivative of x to the third is 3x squared. 5 is constant. What do we do with constants? Vary it. We just multiply. Y squared is constant. What do we do with constants? Just multiply. So our delta z, delta x, 5 is constant. The derivative of x to the third, I don't know why this is blue and this isn't. The constants just carry along, follow along as constant factors. We're finding the derivative with respect to x. X is the variable, y is constant. But wait, there is another, like skywalkers. Although like a reasonable amount of skywalkers. It's going to be 2 of them, just 2. Not like any extra ones. We'll apply the same thinking. If I want to know dz dy, 5 is constant. We just keep it. X to the third is constant with respect to y. The derivative of y squared is 2y to the first. Applying the same thinking, just switching the constant from y to x. Switching the variable from x to y. In each row, y was a constant. Because y and x are both independent variables. Z is a function of x and y as independent variables. Implicit differentiation is for when x and y are related. When we're including x and y and we're thinking about a curve, x and y. That's a great question because we're going to have to be able to distinguish which one is going on. In this case, we're thinking of x and y as being independent variables. Z depends on x and y. When we're doing implicit differentiation, x and y are related in some fashion. They're related by the equation that we're given. perfect timing, that is always the question that needs to come up at this point. When we apply implicit differentiation to an equation, the read on that equation is that x and y are we're describing a relationship between x and y. Here, we're thinking of x and y as being independent of each other. So with this function of two variables, with z as a function of two variables, we ended up with two derivatives. Neither one is a complete description of how z is changing. One, the dz dx is just how z is changing with respect to x. Dz dy is just how z is changing with respect to y. So they are derivatives, but they're a different kind of derivative. We call them partial derivatives because they're only giving us part of the story about how z is changing. So we say these are partial derivatives. We get two partial derivatives, one for each variable, one for each independent variable. Also, delta z over delta x is only going to work if z is like a linear function. We want not average rates of change, we want instantaneous rates of change. So we're going to say, instead of delta z over delta x, we're going to say dz dx. But we're doing partial derivatives, so we're going to write a different version of d. So instead of saying delta, we're going to write dz dx. We use a fancy modified d for partial derivatives. But we still say d, dz dx. It's not quite a delta because a delta kind of comes around and loops back. This is a lowercase delta before it gets bumped and gets that dent in the upper part. If you don't know what I'm talking about, you bump into the d to get like that dent to make a lowercase delta, it's probably better. If all of a sudden you're like, oh wow, I'm starting to see things like Leach sees them, that's the time to like go, oh no, that's bad, and then like run away.
Yes, the math makers.
Yep. So we'll say dz dx and dz dy. The point that I want to make is you already have the mechanics in place. You already understand what derivatives are trying to tell you. We're just adapting it to functions of two variables. We had all this thinking in place. We're just adapting it to a new thing. Incidentally, if you're wondering what would happen if we had a function of three variables, we would just have three partial derivatives. It would be hard to picture because a function of three variables is going to be a three-dimensional solid in four-dimensional space. And now it's hard to picture. But instead of a line being extended infinitely, then a plane extended infinity, it'd be this like a cube extended infinitely. And it doesn't take up the whole space because it's going to be sitting in four-dimensional space. Right? Yeah, it's hard to picture, isn't it? Some of you are like, oh, no, I could totally picture it. I saw the MCU, I saw the Tesseract. I know how it works. Like, well, that's just a 3D projection of a 4D cube, hypercube. That's the best we can do with our puny 3D mind. Any questions? Now, in this case, the X and Y, when we treated them as constants, they were constant factors. They were included by multiplication. If I want the partial of z with respect to x, x is the variable and y is a constant. When I look at this and I see y squared as a constant, how is it this function different than the previous function? How is y included? How is y mixed with the x in this function? We're going to want to find dz dx. And we're going to want to find dz dy. With respect to x, 5 is a constant factor. I wasn't being specific before because everything was just being multiplied together. Now we have to think about it. In this problem, with respect to x, 5 is a constant factor. X is our variable. But then we get a plus. This 6y squared is a constant, but it's not a constant factor. How is 6y squared included? It's like a c. It's a constant term. In this case, the 6y squared is a constant term. What is the derivative of a constant term? Absolutely nothing. I like that. It's very dismissive. Absolutely nothing. So in this case, 5 is a constant factor. With respect to x, we have multiple derivatives, so we can't just say the derivative of. It's got to be with respect to something. But the 6y squared is a constant term. The 6 and the y squared all mashed together. That's a constant term with respect to x because of this plus. With respect to x, 6y squared is a constant term. The derivative of a constant term is 0. So the derivative of 5x cubed is 15x squared. The derivative of plus 6y squared, no x's in that, it's constant, is 0. We wouldn't write that. I'm just trying to emphasize that. I almost wrote an exclamation point after the 0, as if to be shouting. But you have to be careful because when you would read it as 0 factorial, it's like, oh, well, if the derivative of a constant is 1, which is equal to 0 factorial, then why did you write 0? We have to say it calmly. So if z is 5x cubed plus 6y squared, with this knowledge, what would the dz dy equal? Yeah. 12y to the first In this case, 5x to the third is a constant term with respect to y. Questions? We've already got mechanics in place. We're just adapting it to this new scenario. It's like Karate Kid scenario. In Calc 1, you like learn your maneuvers, nx to the n minus 1. That's like paint the fence. And now in Calc 3, I'm throwing punches, and paint the fence is still the same maneuver. There was a newer version of Karate Kid, and I haven't seen it, so I can only reference the Ralph Macchio. It was wax on, wax off. It was paint the fence. Any question? Yes.
So it's 0 because of 6.
Because of the plus. Oh, we look at how the y is included with all this x's, and because we hit a plus, it would be the difference between 5x cubed, 5 times x cubed, and x cubed plus 5. How's everybody okay? This is not complete. We talked yesterday about what integral of a function of 2 variables should represent, and it should be a volume under a surface and above some region. Right now, where the function is the height, I've got a height and I've got dx. That's not volume. I need something else. What else am I going to include to make a volume? I need 3. I got my z. I've got my x in my dx. What else do I need? A dy to get a width. My kerning was terrible on this one. Now I got a volume. 5x, I got my function, 5x cubed y squared, that's my height. Dx is going to be a depth or a length, and dy can be my width. That gives me 3, that gives me a volume. That's our thinking behind this. Presumably in these 2 integrals, I would tell you the different values of x's we're going to integrate in between and the different values of y we're going to integrate in between. That's a detail that we'll talk about later. I'm just doing inception right now. And you'll think of it later. And I don't know why I have to do this. So we end up with this double integral. There's our height, length, width. And we want to find the antiderivative of this function. What's the first thing that we're going to treat as a variable? Just use your instincts to read this integral. I'm looking at 5x cubed y squared. What's the first thing, the first variable that we run across? X, because it's inside, it's closest. We know here's our function. The first thing that the function runs into is the dx. What is the integral of this function with respect to x, even though I haven't ever explained what the integral of a double integral or how double integrals work? I don't care that I've never explained how double integrals work. You already know. What's the antiderivative? Integrate with respect to x, please.
Do we do partial derivative?
We're not derivating. We're integrating. What about the y squared with respect to x? What's that? It's a constant. We're thinking dx,
So
y squared is constant.
Oh, constant.
Anything else? What else? We're gonna have to antiderivative with respect to y. Are we done antiderivative thing? That's not a verb. It is now. Antiderivative with respect to x.
Oh, there's still a C.
There's still a plus c. We might have taken the derivative with respect to x and ended up with some constant. I'm going to label it C1 since we're going to be doing some more derivative. Then we'll get into some details if you happen to notice. Or we'll see how much I can get away with. What haven't we done yet? Still haven't done that part. We're just doing things a one at a time. I didn't tell you that you could do this one at a time. I just hope that you would try. See? And it seemed to be working out. I ain't even mad. I wouldn't go through and write all this and say, that's not how it works. You're all wrong. Now feel badly about yourself. Ha ha ha. I mean, that would be a typical math teacher move, but I mean, that's just not my style. I'm going to clean this up because this is kind of a mess. So I want to integrate with respect to y 5/4 x to the 4th y squared plus c1, whatever that happens to be, and I'm going dy. So now what's the integral of 5/4 x to the 4th y squared plus c1 with respect to y? Don't be fancy. Slow is smooth and smooth is fast. 5/4, that's a constant factor. So we're going to carry it. X to the 4th with respect to y, that's a constant factor. We're going to carry it. What's the integral of y squared with respect to y? 1/3 y cubed. What's the integral of this constant c1 with respect to y? Just multiply by y. Whatever that constant is, just multiply by y. And what else? Oh, I was about to write something else. What am I going to write? C2. I was actually going to go with C3, but C2 is even better. I like that. Look at all the mechanics that you already have in play. Now, there's some big mysteries here. It's like, oh, dude, what are these two constants running around? What if instead of saying dx dy, it said dy dx? Would that change things? Are these two constants really just two constants? Because it looks like I've got this plus c1y and then this c2 constant. What if these were the other way around? That's going to mess with what shows up. Like x's are going to show up and shit. What the heck is going on now? Doesn't matter. We're just focused on what the moves are. The moves that you already have. Now we should clean this up a little bit. 5/12 x to the 4th, y to the 3rd, c1 times y plus c2. That's very unsatisfying for us right now. The reason I'm pointing out how unsatisfying having c1 and c2 out there is to try to make you think about it. I'm trying to do Inception to make you bothered by this c1 and c2. They're not. Because remember, this first c1 showed up when we were integrating with respect to x. So it's constant with respect to x, which means it might be a function of y. C2 showed up as an integration with respect to y, so it might be a function of x. There's some fishy shit going on now, but we've got maneuvers. But that does raise a question. We did things in a certain order. What if I changed the order? How does that change?
Really change. It's changed the big sum.
Something's gonna change. Something might change.
Is the C1y that base take C1x?
Now, we can sum up all the rest of multivariable calculus and make it just snap into place right now. But only if I explain what's going on if I switch the order right now. I mean, I have to do it right now. If I wait until Monday, then it's just going to be a struggle to get through multivariable calculus. So let me clear up all the confusion so that multivariable calculus becomes trivial for the rest of your life. Oh, darn it, look at the time. I guess we're going to have to wait until Monday. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing. And if you didn't see that coming, you just haven't been paying attention to how this class operates.